Hello, it's Dr. Ellis here with Uncertainty with Measurement. Not the most glamorous bit of biology we ever do, but we're going to look at why we have uncertainty, and that's what I'll do first. And then we're going to look at what we do when we have to combine uncertainties. So when we're dealing with uncertainties, again, I'll show you what I mean in a minute. So I asked my class a few weeks ago to measure lots of pumpkin seeds, and I put them on graph paper. And if it's on graph paper, that's really useful because we use 2mm graph paper generally, so that's 2mm. So they had to measure all the size, all the maximum lengths of the seeds, and then we did some frequency histogram work to show that it follows a normal distribution. It follows that bell-shaped curve. And when I asked them to measure this, these are what people inputted into my Microsoft form. These were their measurements. Now, some of these are quite a way off. I mean, if I say that that's 0, that's 2mm, 4, 6, 8, 10, 12, 14. Well, it's more than 12 and it's less, sorry, it's less than 12 and more, I'll get this right. It's more than 12 and less than 14. If I was a betting man, I'd say quickly, I'd say, right, 13.5, because that's 13, isn't it? So, I'm round about the 13 mark. Okay, so when I look at their data, and here's their data that they entered, I can think, right, well, I'm not, if I was calculating a mean, I'm not going to count that one and that one and that one, and that one. I think those four there, they look like proper anomalies. I can't see how anyone would measure 12 or less than 12 looking at that seed. Maybe they measured seed 0, 1. Okay, so I mean, and it just goes to show why we have to quote errors, because there's a massive range. Everyone's measured exactly the same seed on exactly the same background, and once I get rid of the anomalies, it's going between 13.0 and 13.9. I think when I zoomed it in really, really high before and did as accurate as I could, I got it to be about 13.7. Okay, but let's say I'm gonna a good educated guess, I think, is 13.5mm in terms of weighing up this. Yeah, it's slightly more than 13. Yeah, I'm gonna go 13.5mm. Okay, however, that's not including the fact that I'm having to kind of like guess a bit in this area. Quite frankly, I'd have to guess here as well on this end, but I'm assuming that I'm not going to have to guess at that end, that end is fixed. Okay, and it's on a line anyway, so I can kind of forget about that area a bit. Again, it gets a bit debatable when I have to kind of worry about that end as well, but we'll get to that in a future lesson. So yeah, here I'm guessing because I can't see the scale. I could get a higher resolution measuring equipment, but currently I'm stuck where I am. Okay, so it makes sense to say, well, it's 13.5mm. However, I'm saying that there's a potential error of, I'm going to go for 0.5mm. Often written like that in brackets as well to show that it's all in millimeters. So I'm saying it's 13.5mm. However, there's an uncertainty of 0.5 mm. Yeah, because the resolution of the human eye and everything, and the fact that it's a millimeter scale. Sorry, it's a 2mm scale, means that that's probably where I'm at. So yeah, if I put anything between 13 and 14, I'm going to class that as, yeah, that's in the realms of kind of error. Okay, and that's kind of what we got. They range from 13.0 to 13.9. Okay. So from all this, all we need to be aware is that when we measure anything, there's a certain amount of error. Okay, and we can reduce that uncertainty by using other equipment. I could use 1mm graph paper. I could use vernier calipers, anything like that, and I could get to so there's less uncertainty. But every single piece of measuring equipment has a certain level of uncertainty, and I'd have to decide in this experiment where I'm basically just measuring the length of seeds, is this level of uncertainty acceptable for what I'm doing, or do I need it to be smaller? If all the seeds are kind of like 13.5mm long-ish, I'd probably my uncertainty would be too big. But when we did this, they range from like 9mm up to like 17mm anyway, so it didn't really matter. So we're just going to look at another example now, just to kind of go through. why we need this. Again, you can see I've got a nice version here where we're trying to measure this piece of red tape. And again, if I was measuring it, I'd say, well, that's 2.3 centimeters. It shouldn't really be U centimeters. Should be, it's the unit of the devil. So let's change that. Yeah, so let's go for millimeters. So it's going to be, it's 20. So that one here, that's 23 millimeters. Yep. And then I just say, well, it's 23, and I'd probably say 0.5 plus or minus 0.5 of a millimeter. Yeah, pretty similar to the one before. Okay, again, that does assume that this edge is lined up perfectly. If I was trying to measure, you know, the length of a bird's wing and it's kind of moving in my hand, then I'd have error on both ends of my measurement. So by measuring with rulers, you can end up with double the error compared to the example below. So the example below, zoom into this, over, out of the way a bit. So yeah, so this is a thermometer. Again, it only has one end to read from, and then I'm just saying, well, yeah, this is 20, 1, 2, 3. I'd probably say, oh yeah, that's 24 degrees C. Okay, or I could say it's 24 plus or minus, and we're probably saying again 0.5 of a degree C. Okay, so we tend to pick that at the halfway between the unit when we're doing this. Again, this is miles more important in a science like physics, where there's hardly any variables. It's very, everything's highly controlled, and therefore, and they're just trying to, measure very small differences. In biology, if you imagine I've got a water bath with a test tube in, I'm pre-incubating some enzyme solution. And my thermometer's in there, it's in a water bath, and then I'm going to add that to another one that's in another water bath, mix them together and record the rate of reaction, and record the rate of reaction by saying how long it takes for a color change to appear. There's so many variables that the actual error on the actual thermometer is minute compared to the error in the experiment, where I'm having to kind of adjust the temperature of a water bath, maybe with a Bunsen flame, so it's getting too hot and too cold. Again, the actual thing that we put there is very, very, very kind of rarely put down. It tends to be something that you'll kind of quote as like a little asterisk at the bottom of a table rather than including it in your data. Anyway, we're going to look at next how we combine uncertainties. Right, so back at the seed now. Sorry if that jumped. Let's assume now that I want to measure the area of a seed, and my assumption is going to be that it's the area that the seed would fit into if it was put into a rectangle and it was kind of at like a normal to the actual box. So it's not put in on a diagonal; it's put in perfectly lengthways. And I'm going to use this to estimate the area of seeds to compare area of seeds. I don't know why we'd want to compare the area of seeds, but who knows? Maybe we do. Okay, so I can measure its maximum length. So this edge here, I can measure that. Let's assume I've got that, and I've done it really carefully. So that's 13.7 millimeters, and I'm going to write that as 13.7 plus or minus my potential error. My uncertainty, I should say. So that's the length equals, and the width equals 1, 2, 3, 4. Okay, and the width equals 4. Oh, it's not 4, is it? It's 8. Oof. 8, because it's a 2 millimeter graph paper. 8 plus or minus the same amount of uncertainty. Okay, so those are my measurements. So now I want to know, well, what's the area? Well, I can do 13.7 times 8 to get my answer as he reaches for his calculator desperately, because that's always to hand, like yours are always in class. It's always good that everyone's always got their exam calculator with them, so they get to use it. So that's 109.6 millimeters squared. But what do I do with the uncertainty? Because I've still not done anything with these. Well, they set rules of what to do with uncertainties when we combine uncertainties, because I'm multiplying two numbers together. So this is the tricky bit, and this is what we're going to go into next. It's not a case of just adding them together, okay? It's not a case of multiplying them together. There's a whole set of rules for doing 3 types of combining uncertainties. There's one when we are adding values or subtracting values. There's one for multiplying values, and there's one for dealing with squared and cubed units as well. So that's what we're going to have a look at next, and it means zooming to this worksheet. Hopefully, worksheet even. Worksheet is completely different. Okay, right, so how will it be asked in a biology exam? So this is the sheet that is attached. So you should download this sheet. Ideally, you can print it off, but if you can't, it's actually reasonably easy to do it just via a screen and kind of work them out on a piece of paper anyway. This is where in biology some of you will be math, do loads of maths, and therefore you don't need any help from me. So just in terms of this, the rules are at the side. It goes through adding or subtracting values. So this is where the uncertainties should be added, and therefore, if you add or subtract, you always add the uncertainties. So that's relatively straightforward. Again, some of you can just crack on with this sheet, and you don't need me to kind of go through it with you. And I'm not a math teacher, so this is like a biologist trying to do math. So it's never going to be my favourite thing ever. As in, it's not what I'm good at. I'm better at other things, but I can do these, so don't worry too much. I can do A-level maths. I've got A-level maths even as well. Multiplying or dividing, this is where you have to convert it into percentages first. So I'm going to go through one of these examples, and there's a work through example here as well. But again, some of you can just crack on with this, and then there's a power rule one. So some of you, can just read these and have a go, and then there's another file on there that's got the answers to these as well, so you can check if you've got the answer right, then you know you're doing it correctly. I think they've asked this in exams twice now, and it's been worth 2 marks out of the entire exam series. So, is it worth spending hours and hours and hours on this if you're not getting it for 2 marks? Possibly not. But then again, it's a relatively straightforward 2 marks if you know the rules. Okay, so we're just going to have a look at adding or subtracting values first, and then we'll have a go at one, and we'll have a look through this one first anyway. So again, I like to highlight the odd bit, especially numbers. So the uncertainties should be added always, never subtracted. So the leaf on day 1 was 5 centimeters long, and the leaf on day 2 was 7.2, and therefore I've got the difference. It was saying, how much has it grown by? Well, it's grown by 2.2 centimeters, and you can see that the uncertainty was always a millimeter, 0.1 of a centimeter, and they've just added those two together to get the final answer. Okay, so let's have a go at one. There's one here. So it says the baby's heart circumference at birth was 50 centimeters, plus or minus 0.1. By 1 year old, the circumference had increased to 7.5. What is the increase in the head circumference over that time? So the increase equals, so it's 75 minus 50 equals, it's increased by 25 centimeters. Okay, so that's that part of it done. I've used that number and that number. Okay, and now I'm going to switch to using the uncertainties. They're both plus or minus 0.1. This is just I've taken one number away from the other, but we always add the uncertainties. So therefore, the uncertainty is, so uncertainty equals 0.1 plus 0.1, which equals 0.2. So if I was going to write the answer down, so the answer now equals 25 plus or minus 0.2 in brackets centimeters. Okay. In exams, they tend to ask you to work out the uncertainty, and we call this the absolute uncertainty because it's not a percentage. As we'll see on the next one, we have to get into percentages. Okay, so yeah, these are easy. If you're adding or subtracting numbers, then the actual, you always add the uncertainties. And that's probably the main ones that we do. So let's have a look at the next example. So these are, again, probably the next most common. So what do we do for the numbers? I highlighted it in yellow, didn't I? So let's do the same. So it says the percentage uncertainties should be added. Yeah, crucially, it's saying now, that it's the percentage uncertainties should be added. Yeah, not the actual uncertainty. So we have to work out a percentage uncertainty, add them, and then turn it back into the absolute uncertainty. You'll see. Go along with it. This is how maths works, isn't it? When I was at school, it was teacher goes through one or two, and then you have a go at some. And we're going to do the same here. And if this isn't sticking, pop along to workshop next year, and the teacher goes through it. Yeah, and quite a few students come to workshop with this because they struggle with this percentage bit. So it says the heart rate is 70. That's beats per minute. That makes sense. And we've got an uncertainty of 1 beat per minute. So when they were calculating it, they've timed the heart rate for a minute, but there's that, do I count that last heart rate or do I not count it, as it kind of ticks over to a minute, and therefore it's quite normal to have plus or minus 1 minute. Okay, so then they've worked out the percentage uncertainty of heart rate, and all they've done on this value here, again I'll do it in green, so from here they've done 1 divided by 70 times 100, and that comes in at 1.4%. Okay, so that's more a percentage uncertainty, 1 over 70. Okay, next is the stroke volume. So they're trying to work out the what's it called? Heart rate times stroke volume is the cardiac output. It came, it's there underneath. There we go. Yeah, so the stroke volume is 0.08 decimeters cubed. Okay, and plus or minus 0.005 decimeter cubed. A decimeter cubed is a litre, remember, or 1,000 centimeters cubed. So then they've got the error here of 6.25 just by doing 0.005 divided by 0.08 times 100. So that's where that number's come from. And just to make it really clear, that's the 0.08 that's over here, and that's the 0.0, and that's the 70 that's over there. Okay. Then, as you know, cardiac output is 70, the heart rate, times by the stroke volume, the volume of a ventricle, and they both have the same volume. And then that comes in at 5.6 decimeters cubed per minute. Yeah, I've combined my units to get the answer. So that's what even that can get a couple of marks on an A-level paper. And then remember, the rule is that the percentage uncertainties should be added. So my percentage uncertainties were 1.4 and 6.25. 1.4, 6.25 from above. Therefore, my total percentage uncertainty is 7.65. So the absolute uncertainty is 0.4. So where's this 0.4 come from? Well, this just comes from the fact that, oops, wrong pen. Sorry about that. There'll be lots of that normally. So my answer of 5.6 from above times by 7.65 divided by 100 equals 0.4. Just check it before I say that that's true. Times by 5.6. 0.4284, but I'm quoting them to the same number of decimal places as the answer. Okay, so the actual answer, what I would write down is the cardiac output is 5.6 decimeters cubed plus or minus 0.4 decimeters cubed per minute, and that's all in decimeters cubed per minute. Okay, so that's where the 0.4 comes from. Yeah, we've worked out the percentage uncertainty for each of the individual original values, Then we add them together to get 7.65. And then we have to relate this back to the final answer that we've got as well to find out. Yeah, so within this 5.6 decimeters cubed per minute, this 7.65% of it is uncertainty. So that boils down to 0.4 decimeters cubed per minute. So that's a proper hard one. If you can do that, there's no problem. I think the hard bit is remembering what the rules are, because quite frankly, I have to come back every time to kind of come back to these. So let's have a little look at one and see how we do. Again, you can use highlighter pens in the exam, so why don't you use them? You just can't use them in your answer. So given that the pulmonary ventilation rate, the PVR, is calculated by multiplying the tidal volume by breathing rate. Yeah, so tidal volume, remember that's the amount of air that's been exchanged in per breath. It can change, can the tidal volume? Because a deep breath is less than a small breath. It's what you are breathing now. And that's multiplied by the breathing rate per minute. So it's similar to the cardiac output, but for lungs. So calculate the pulmonary ventilation rate from these data. So the tidal volume is 2.5 decimeters cubed, and the rate is 15 breaths per minute. So let's do the easy bit first. That the so PVR equals tidal volume 2.5 times by 15, and that equals 37.5, and that is in decimeters cubed, liters per minute. Okay, so that's the answer for that. But now I need to use the error. Sorry, the uncertainty. I keep calling it error. It's kind of interchangeable, but technically different, I guess. So now I just do, right, well, let's do the tidal volume first. So TV equals, so I've got 0.2 divided by 2.5 times 100. Let's check that. 0.2 divided by 2.5 times 100, 8%, which equals 8%. And the breathing rate, BR, equals 1 divided by 15 times 100, which equals 1 divided by 15 equals times 100. Don't forget to times by 100. Almost didn't do that then. That's 6.6 recurring percent. That's the kind of number I store in my memory. Then what do we do with this? Well, we then add them together. So we add these together, and that comes in at, so I can recall that, plus 8, which equals 14.6 recurring percent. So 14.6%, 14.6 recurring percent, sorry, of 37.5 is my absolute uncertainty. So my absolute uncert equals 37.5 times by 14.6 divided by 100. So 14.6 recurring. Don't forget that, because it might have an effect. You can lose marks for incorrect rounding. Was that times 37.5, which equals 5.5. Exactly. 5.5. So the answer, so the overall answer equals, it's 37.5 plus or minus 5.5 decimeters cubed per minute. You can see why we don't tend to quote the uncertainty, because it makes the answer messy and less understandable by the general public. Okay, but again, when you ever go at one of these, and I'm going to carry on going through these, so you can just kind of come back and watch me talk through them. But there's nothing better than working one out for yourself. So maybe stop the video now and have a go at the rest and see if you can do the rest. Yeah, if you're still unsure, stick with me. Right, I do apologise for the by the way. I'm very my person when I'm doing these, because I'm having to think about pressing certain buttons at the same time. I'm normally a bit more fluent when I'm in front of a class. Anyway, power rules, like squared and cubes. So this time we multiply. This is interesting. We're going to multiply the percentage uncertainty by the power. Right, so a section through a dandelion stem is measured to have a diameter of 7 plus or minus 0.5. So we've got 7 and 0.5 of error, uncertainty, sorry. What is the cross-sectional area of this stem? Right, so the radius is 3.5. Oh, so we're obviously going to use pi r squared here, aren't we? So area equals pi r squared. And they always say assume that pi has no error, or sorry, has no uncertainty. Yeah, so the radius is 3.5. Just because I've halved the radius doesn't mean I do anything to the level of uncertainty. If I was measuring the radius with a ruler, I'd still have the same level of uncertainty. Does that make sense? If that seed from before was smaller, I still would have had the same level of uncertainty at where I'm reading from on my ruler. Okay? So then we've worked out the percentage uncertainty in the radius. So how have I got 14.3? How have I got 14.3? Yeah, so that is 0.5 divided by the actual. Okay, comes in at 14.3. Let's check that. 0.5 divided by 3.5. Oh, it is times 100. Yeah, 14.285. So it's rounded to 14.3. So that's the percentage uncertainty in the radius. I want to know what's the percentage uncertainty in the area. And the rule was, as I highlighted at the start, we multiply the percentage uncertainty, I've got that, 14.3, by the power. Yeah, well, the power is the power 2. It's r squared. So all I've done to get 14.3 into 28.6, you can probably see it, is that we've times it by 2. Okay, I've times it by the fact that the radius has to be squared. So here I can just put, yeah, that is 14.3 squared. That's how I've got that. So then it's how do I get to the absolute uncertainty? Well, this is when I just use my 28.6. That's uncertainty again, and we apply it to the total cross-sectional area that I've worked out, the 38.5. So this is where we do, it's 38, oh, I've done it again. So it's 38.5 times by 28.6%. So let's do it, 28.6 divided by 100 times by 38.5. Yes, 11 millimeters squared. So again, the answer that I would give, let's have to push this up slightly because my hand's going to hit the stop button if I don't. So yeah, the area equals 38.5 plus or minus 11, and that's all in millimeters squared. Okay, so let's have a look at one. That's one of them. Yeah, so here's an area one. Again, it's very, very similar. It says the radius of the field of view is measured using a stage micrometer at a magnification of 40 to be 2.1 plus or minus 0.2 millimeters. Calculate the area of this field of view. Note the uncertainty of pi is taken to be 0, so they tend to say that. So let's look at our numbers. I mean, the good thing about this is that we've only got 2 numbers to deal with. The times 40 is irrelevant because it's saying calculate the area of this field of view, at times 40. So there to get us started. So let's do the area first. So the area equals pi r squared, which equals pi times by 2.1. Oops, is it 2.1? Oh yeah, it is, because it says the radius. There it says radius of the field of view is measured to be, so it's made it easier for us. So 2.1 squared is that times by pi which equals 13 and we've measured it to 1 decimal place here, so I'm going to do the same. That's 13.9 millimeters squared. Okay, I'm saving that number in my memory so that because I'm going to have to use it again, and I'm going to use it. I'm going to use it in its raw form, not its rounded form. So the insert, that's a C, sorry, equals. So I need to work out the percentage uncertainty first. Is 0.2 divided by 2.1 times 100. So 0.2 divided by 2.1 equals 9.5%. Again, that's me rounding it. It's 9.52. Then I need to times that by 2. That's the power. Times 2 equals, so that's 19.0%. Okay. And then I need to go to the absolute uncertainty. Absol uncert equals 19% of my final answer. So 13.9 times by 19% equals, so I divide that by 100 times by my original, which comes in at 2.6, equals 2.6389. So my answer equals 13.9 plus or minus 2.6 millimeters squared. I'm going to take a break there now, and I'll come back and finish off the rest, which again you can watch through, or hopefully now we've been through 3 examples, well, kind of 6 examples, 3 that were written at the start, and 3 we've done for each one. I think on this sheet there's how many left? Is there just 3 left? 4 left. 1, 2, 3, 4. So if you can do those 4, then you know you're combining uncertainties, and therefore you can get 2 extra marks in an exam now that you couldn't have got previously. Okay, I'm going to come back in a bit. And I'm miraculously back. Amazing. Right, I'm going to do these a bit faster. So again, if you're happy, hopefully you've pressed on. If not, let's look at one. So the PVR, the pulmonary ventilation rate of asthmatic, reduced from 37.5 to 23.4 decimeters cubed per minute. Oh yeah, or did I have asthma attack? That's why it's reduced. Don't know why I've changed to green there, because I was using yellow when for the numbers. Number, and the uncertainty is 5.5 and 4.5. Calculate the decrease in PVR due to it. So decrease. So we are at 37.5 minus 23.4 equals 14.1. That's my yellow bit, and my green bit it's gone from, so the uncert equals 5.5, and I've got a 4.5. Remember, we add them, even though I've deducted those 2 values. So that's a plus, that's a minus, we add them together. So plus or minus 10, plus or minus 10. So a massive load of uncertainty in that value, decimeters cubed per minute. But yeah, nice and easy. Again, the thing to remember is you always add your uncertainties, even if you're subtracting your other values. So C is a nice easy one. Again, you feel it's too easy. Again, in the exam, you'd know it was easy because this would have just 2 marks associated with it, whereas the other ones where you have to do the percentage and things, where there's more steps in the calculation, it's going to mean that there is a greater marks awarded. So next one, E, in an enzyme control reaction, 20 centimeters cubed of gas were produced in 60 seconds. Calculate the rate of reaction over this period. So the rate of reaction is always something over time, isn't it? So we've got 20 and 60, and it's same level of error, uncertainty. Okay, I'll get back on that in a minute. So yeah, so we've got so it's 20 centimeters cubed. I mean, it doesn't say what unit to calculate, but let's just keep it as it is now. So that's per second. Let's not get into unit conversions as well. Oops, it's not a -1, is it? Because I just divided by a second. So that equals 0.3 recurring centimeters cubed per second. So that's our rate and our uncertainty. Well, I've divided these numbers, haven't I? And remember, when we divide or times, let's go and look at the rule. The percentage uncertainties should be added. Okay, so I should do percentage uncertainty again. So let's do the percentage uncertainty. So I've got 1. Oops, pick a pen. So we've got 1 divided by 20 equals 5%. and we've got 1 divided by 60 equals 1.6 recurring percent. Okay, and therefore, what do we do to those values? We add them together. Therefore, total uncert equals 6.6 recurring, and therefore the absolute uncert equals 0.3 recurring times 6.6 recurring. So it's a pain with the recurring percent. Oh, looks like I've lost my calculator. There it is. So plus 5 equals over 100 equals that times yes, that's 0. It comes in at 0.02 recurring. So my answer, it's a bit of a horrible answer, sort of a fine answer. Remember, in the exam, they'll have a little line for you to write this. Equals 0.3 recurring plus or minus 0.02 centimeters cubed per second. Done. Happy on that. Have I got it? Have I got it right? I'm just check me. Oh, I have. Yes, good. So that's E. Again, that's the first one where we've had a divide sum and we added the percentage uncertainties together and had to do this absolute uncertainty. You can see how, in an exam, there's, well, I probably get a mark for coming up with the units, I guess. 1 mark here, there'll be 1 mark for working out the percentage uncertainty, and there'll be another mark for applying that to the final question, so potentially 3 marks or even more, because there's more to do. Next, yeast suspension in anaerobic conditions has a temperature of 21.1. Yellow, 21.1. When oxygen was bubbled through to make the conditions aerobic, the temperature rose to 24. Remember these, it's fully using the sugar, more heat is produced. Calculate the increase in temperature. So this is a nice, easy one. It's just working the increase. They're all both in degree C, so it's nice and easy. The increase is 24. Yeah, so 24.0 minus 21.1. I encourage you to write stuff down. Again, you can see it's easy to kind of like, which equals 2.9 degrees C. It's easy to kind of pick the wrong numbers. It's why I'm highlighting them in yellow. So that's my yellow bit. And now, so that's my yellow kind of calculation. Now I'm going to do my green calculation, which is the rest. So I've got 0.5. I remember we add the uncertainties, so plus 0.5, the both 0.5, which equals 1.0. So my answer equals 2.9 plus or minus 1.0, and that's degree C. Yeah, that's the increase in temperature due to aerobic conditions. Again, nice easy one. Couple of marks for that one, not 3. Last one, Q1. Excellent. I tried to give you every kind of possibility when I came up with these questions. So the radius of a spherical nucleus was 3.5, and the error of uncertainty of 0.5 micrometers. Calculate the volume, given the volume of the sphere is 4/3 pi r cubed. So the volume, there you go. It's been 5 minutes since I last did that. Volume equals 4/3 pi. R is 3.5 cubed, which comes in at 179.6. And that's now in micrometers cubed. Right, the uncertainty. I've got 0.5. And I need to work out the percentage first of all. So divided by 3.5 times 100. Just to remind you, that's my green number. That's my yellow number from above. And that comes in at 0.5 divided by 3.5. 14.3. Yeah. equals 14.3 plus 14.2857. So I'm storing that number. So that's percentage error. Now, what's the rule? Well, we multiply it by the power, and the power is 3 because we've cubed this unit, haven't we? It's 4/3 pi r cubed. We're cubing the radius. So we times this by 3. So then it's just times by 3. I've not rounded that number in my calculator, so that's 42.9 is my uncertainty. So that's, and therefore I then have to percent, and therefore I need to divide that by 100 and times it by 179.6, comes in at 77. So yeah, 179.6 times by 42.9 divided by 100 equals 70. Oops, not 70. Oh, it is, yeah, 70, 77, 77.0, sorry. Rounded up to 1 decimal place. And therefore the answer, which is just write it all out again, 179.6 plus or minus 77.0, and that's in micrometers cubed. So we're done. 40 minutes. Oh, yeah. Again, if it's making sense, I guess that's all we need to be. And the final tips are, learn your rules first of all, and what else was I say then? Mine's got blank. Too much maths. Mine goes blank. I'll leave it there because I'm just waffling.